Okay, welcome to our second virtual classroom. Just like as we did last week, we're going to start with a review. So this is a review of the material that we went over last week. So last week we moved from talking about mirrors, where light is reflected, to talking about lenses, where light is refracted. And if you remember, we talked about the fact that light travels at different speeds in different mediums. So when light hits a transparent medium, this causes the light to refract. So let's do a little bit of a review. Let's say above the line we have air. Below the line, the medium is glass. This is our incoming light. Okay, so this is our light source. We'll go ahead and draw our imaginary perpendicular. Okay, and we learn from the law of reflection that the light will be reflected at the same angle as the angle of incidence. So here is our angle of incidence, and then this is our angle of reflection. But then as it encounters a different medium, if that medium is denser, this light is going to bend a bit, and this becomes our angle of refraction. All right, so if we go ahead and name these angles, let's say this is theta 1, theta 2, this is theta 3. Should have made my drawing a little bit bigger. My angle's a little bit bigger. According to the law of reflection, theta 1 will always equal theta 2. The angle of incidence will always equal the angle of reflection. But theta 1 will not equal theta 3. So the angle of incidence will not equal the angle of refraction if these two mediums have different densities. So then we talked about Snell's law. And Snell's law helps us determine what these angles are. And if you recall, Snell's law is n1 sine 1 equals theta 1, theta 2. Let me just write that over because that looks really sloppy. So n1 sine of theta 1 equals n2 sine theta 2, where this is the angle of incidence and this is the angle of refraction. So what is this n1 and n2? Well, the n is the index of refraction. All right, which is just a ratio of the speed of light in a vacuum to the speed of light in any other medium. And so we can write that like this, where c equals the speed in a vacuum. And then this velocity here is the speed in the other medium. So n1 has no units because both of these are meters per second. The units are going to cancel out. It's just a simple ratio. Okay, so hopefully you remember all this from last week. So let's look at it on your own that use this index of refraction. Actually, we're going to look at a couple of them. Let's start with 12.4. I know you've done this in your homework, but this is just going to be a review, bring you back up to speed, talk through how we do the problem in case you had any questions. So I'm on page 405 in the book. On your own 12.4, it says the index of refraction of water, so the N of water is 1.3. Again, no units because it's just a ratio of two speeds. And the question asks, what is the speed of light in water? Okay, so there wasn't really an example that went over this one, this type of a problem, but if we know N equals C over V, then the speed of light in water is this V. That's what we're trying to solve for. So I can rearrange this equation and say that my speed of light in water equals C over the N of water. All right, remember C is the speed of light in a vacuum. Well, we learned a while ago that that was 3.00 times 10 to the 8 meters per second. Okay, and the problem tells us that the index of refraction for water is 1.3. And if I do that math out, then I end up with 2.3 times 10 to the 8 meters per second. So the speed of light in water is 2.3 times 10 to the 8 meters per second, which is slower than the speed of light in a vacuum, which is what we would expect, because obviously water is more dense than air. Okay, so hopefully that helps clear that one up. Then let's look at 12.6. It's another application of Snell's law. It says a light ray is traveling through glass. So this is a little bit different because most of our problems tell us that light is traveling through air and then it encounters something else. This one's the opposite. In this case, the light is traveling through glass. Okay, so here's our light source. The light's coming in. We'll draw our imaginary perpendicular here. So this is our angle of incidence. We'll call it theta 1. It's traveling through glass, and it tells us, in this case, that the index of refraction is 1.5. Okay, so again, if you remember from last week, I want to keep all my ones above the line. So here's my theta 1, and I'm calling this N1. Okay, and then it encounters air. Okay, so it's coming from glass, it encounters air. So which way is my light going to refract? So this is a less dense, so my light is actually going to bend this way. This becomes my theta 2, okay, and I will have my N2 down here. So this is kind of a picture of the situation. The problem further tells us the angle of incidence is 34.6 degrees. And it wants us to solve for the angle of refraction. Now remember, we know that N for air is 1.00. Okay, so knowing that, we can then use Snell's law. N1 sine theta 1 equals N2 sine theta 2. I think I'm going to solve this a couple different ways. So here I'm just going to put in the numbers. So N1 is 1.5 times sine of 34.6 degrees equals N2, which is 1.00, equals sine of theta 2. Okay, I can divide both sides by 1.00. So I have 1.5 sine 34.6 degrees over 1.00 equals the sine of theta 2. And then remember, to get our theta 2, we take the inverse sine of both sides. So you'll have to use your second button on your calculator. And if we do all that out, theta 2 should equal 58 degrees. Okay, we're limited to 2 significant figures because of this 1.5. The other way to do this which I like to do, is to solve just the equation for our unknown first. So it would be n1 sine theta 1 over n2 equals sine theta 2. Then I know I have to take the inverse of both sides, the inverse sine of both sides. And then I can just plug my variables in over here, or the values for my variables. So the inverse sine n1 is 1.5 times sine of theta 1, 34.6, all over n2, which is 1.00. That equals theta. And then if you notice, these are the exact same equations. So again, my theta, 58 degrees. So this ends up being 58 degrees. And just if we step back and say to ourselves, is this reasonable? Well, yes it is, because theta 1 is less than theta 2, which is what we would have expected, because since air is a less dense medium than glass, we would have expected the light ray to refract or bend out this way. Okay, so that's just a review of Snell's law. Then we started talking about lenses. We talked about two lenses, the first one being a converging lens. And if you remember, a converging lens has kind of an almond shape as such. And a converging lens, if you look at the picture on page 406, well, let me back up for a minute. We still draw our horizontal. Remember, these lenses have two focal points, one on each side. And a converging lens, well, when we're talking about lenses, we also draw a vertical. A converging lens says that any horizontal light beam coming in is going to exit through the focal point on the opposite side. Okay, so all these horizontal light beams converge on the focal point on the opposite side. Okay, and that's why it's called a converging lens. There's a better picture of this on page 406. Okay, so the three rules for drawing our lines and our ray tracings to kind of predict how this image is going to look as it goes through the end, or through the lens. The first rule is what we've tried to depict here, is that all horizontal light rays will exit through the focal point. And then the reverse of number 1 is all rays entering through F will exit horizontally. And then finally, all rays entering through this center point will exit without refracting. Okay, so if we follow these three rules, we can then predict how an image will look as it goes, as we view it through a lens. So an example of this can be found in On Your Own 12.8. On page 408, we're told a converging lens has focal points that are 8 centimeters away from its center. Okay, so we can draw our lens. Remember, we always draw the horizontal, always draw the vertical. Find our focal points. So we're going to say that's 8. That's hopefully equidistant and is 8. If an observer looks through the lens at an object 5 centimeters from the lens, so we draw our person 5 centimeters away, how is this image going to appear? Is it going to be real or virtual, upright or inverted, magnified, reduced, or about the same size? So let's draw our 3 lines. We'll start with green and say our horizontal line, once it reaches the center line, is going to converge. Remember, we're doing a converging lens, so it's going to go through the focal point on the opposite side. The next line we're going to draw is if it came through the focal point. Okay, so the person is in front of the focal point, so we have to imagine as if it came from the focal point. It would then go there and exit horizontally. And then finally, if it goes through the center point from the same set of eyes on the person, it's not going to refract at all. It is just going to go straight. Okay, and it's pretty clear to see that these 3 refracted lines are not going to intersect. So then we extrapolate them backwards. And we show that as such. Okay. Oh, shoot. I'm going to go off my page. Okay, but it's pretty easy to see that they would actually intersect somewhere back here. So we would draw the head at the point of intersection, draw the body back down to the line, and we can see that the image would be magnified, upright. And because we had to extrapolate the light beams, since they didn't all intersect on this side, whenever we extrapolate the light beams, it's a virtual image. So it should be magnified, upright, and virtual. Okay, so I'm gonna say again, you really need to be neat when doing these drawings. You need to draw things pretty much to scale. It's really helpful if you use a ruler, because I need to be able to follow your tracings on a test. So do it big enough, use a ruler, be neat, all of that. Don't forget to put your arrows here. So that's what we learned about converging lenses. And then we talked further about diverging lenses. Okay, and a diverging lens kind of looks like an hourglass. In real life, these are very thin, but we draw them exaggerated. Again, we draw our horizontal and our vertical. We have a focal point on each side, so that's all the same. What's different is as light rays, horizontal light rays come in, they diverge as if they're coming from the focal point here. So they spread out, okay? So on this side, they're diverging away from each other, okay? Obviously, when we're going like this, it would just be straight. Okay, so there's a good picture of this on page 408. So that kind of shows how a diverging lens works. The same 3 rules apply as with converging lenses. So let me get those rules back up here. Okay, and so here's our 3 rules, and let's look at on your own 1210. So I'm on page 410, looking at on your own 1210, and we're told we have a diverging lens with focal points that are 8 centimeters from its center. So again, a diverging lens looks like this. We're going to draw our horizontal, draw our vertical. Okay, here's our center point. Our focal points, it said we're at 8 centimeters. Okay. If an observer looks through the lens at an object 5 centimeters, so again, this is very similar to our last example as far as the focal point and the position of the observer. If the observer is 5 centimeters from the lens, how will the image appear? Okay, so our first line we draw is horizontal light rays will exit through F. Okay, so we draw horizontal, but now remember this is a diverging lens. So rather than converging on this focal point, they're diverging from this focal point. So my light ray will be refracted like this. Okay, so we've used this focal point already. Put a check on there. Then all rays entering through F. So we've already used this focal point. So let's use this focal point. All rays entering through F, like so, will then become horizontal. Oh shoot, I forgot to use a second color. Oh well. And then finally, all rays entering through the center will exit through the center. Okay, so here are my 3 refracted light rays. Obviously, again, these are not going to intersect, so then I need to extrapolate back. And if I extrapolate back, they're going to intersect about right here. So my image again will be upright, reduced, and again virtual because we had to extrapolate. Okay, so if you get confused between a converging and a diverging, even though we're using the same rules, remember that number 1, all light rays will exit through the focal point. Well, on a converging lens, we're going to use this focal point because they're converging. On a diverging lens, we're going to use this focal point because they're spreading out. They're diverging from each other. The second rule, all rays entering through F will exit horizontally. Okay, when we're talking about a diverging lens, since we've already used this focal point for the first rule, then we're going to use this focal point for the second rule. So go toward the focal point and then it's going to go horizontal. The third rule is easy in both cases. Okay. So in both cases, you're using each of the focal points. Okay, in a converging lens, you're using the focal point on this side for your first rule. On a diverging lens, you're using the focal point on the same side for the first rule. And then you're using, on a converging lens, you're using the focal point on the same side for the second rule. And on diverging, you're using this point for the second rule. So you'll use each focal point once in each type of lens. So hopefully that helps clear that up a little bit. So if you can just keep track of which focal point you've used, that will probably be helpful. Then the last thing the chapter talked about is just a camera versus the lens in your eye, and how God has just made our lenses in our eyes so wonderfully that actually to bring something into focus, the muscles in our eyes can change the shape of the lens in our eyes. So we don't have to reposition or move to see something close up, far away, to the right, to the left. Our brain, and through God's design, just tells our lens to change its shape. Okay? And that happens without us even really knowing or thinking about it. In a camera, the lens has to change position. Okay? So if you've ever seen somebody use a camera with a lens, you've seen them turn that lens thing, and that what they're actually doing is changing the position of the lens. So our camera and the lens in our eye can both bring things into focus. They just do so very differently. In a camera, we have to change the position of the lens. In our eye, we actually change the shape of the lens without even thinking about it. And that's how that chapter ends. And I think we've discussed everything in chapter 12. So this week, you'll have a test over chapter 12. If you have any questions over anything we reviewed, especially if you think it's a question that one of your classmates might benefit from knowing the answer to, please post that on Google Classroom, and that'll be our discussion board. So stay tuned for a new video with regarding the new material.